ahead and talk about 4.2 day 2, try to make this quick. Here are our objectives or our goals. We want to be able to apply the first derivative test, that's review. We're going to use the second derivative to talk about concavity and points of inflection. Those are our 2 new vocab words today, our concavity and points of inflection. And then we're going to apply the second derivative test. So I want to give you a little background. So would you go to the second page of your notes? It looks like this. I'm going to kind of skip the review because it's still a little bit fresh from yesterday. We'll review that again when we get back from break. Keyword here, concavity. Concavity is a very, very specific behavior of a graph that we're going to talk about in calculus. It's going to be really, really important. A graph that is concave up looks like that. You probably remember concave and convex from geometry. This is a little bit different. Concave up would look like a bowl. Concave down would be like a hill. So portions of graphs, and it's easily connectable to polynomial graphs, because if you look at a basic polynomial, you can see portions of the graph that would be concave up and portions of the graph that would be concave down. I like to use the idea of whether or not the graph would hold water if you poured water in from the top. Would a concave up would hold water versus if you dropped water on a concave down graph, the water would run off. So the whole portion doesn't need to be concave up, or the whole domain doesn't need to be concave up. You can have portions of graphs that are concave up. And you can have portions of graphs that are concave down. Okay? So a little bit of background for where this comes from and the connection to the first derivative. Review question from yesterday. How can we tell if a function is increasing? A function, f, is increasing if f prime is greater than 0, right? How can we tell if a function is decreasing? F prime is less than 0. So we know increasing, decreasing on f based on the values of f prime. We're going to use that now in the sense of concavity. So look at a graph that is concave up. And I'll just sketch a picture over here. And I want to know so this is f. Okay, this is f. We're not doing anything magical with derivatives or second derivatives yet. If we were to talk about the slopes on f from left to right, because that's typically how we read graphs. On the left, the slope is very negative, very large and very negative, right? And as I move to the right, the slopes get more and more moderate until it gets to this minimum point and the slope is 0. We good on that? It goes from really negative to 0 and then slowly approaches a large positive. So on a graph that is concave up, the graph goes from really negative to really positive. So on this graph, the question would be, what is f prime doing? The slopes are start negative, end positive. Graph is increasing. So when we talk about the slopes, we would say that f prime is increasing. How do we know? We go from a really big negative value to more moderate negative values and eventually 0, and then really big positive values. F prime on that graph is increasing. Make sense? Okay. So I'm going to take you on another leap. We talked about f increasing. F is increasing when, I'm going to take you back to 70 seconds ago. F is increasing when f prime is positive. So f prime is increasing when, oh man, that's a stretch, isn't it? F double prime is greater than 0. So if f double prime is greater than 0, the graph is concave up. And f double prime greater than 0 tells us that, I know this is a lot, but f double prime greater than 0 tells us that the f prime is increasing. I know. Okay, we'll make this. I'll try to give you a little trick here in a minute. Okay. Similarly, Similarly, let's look at f prime. I'm sorry, let's look at f double prime when it's concave down. Concave down, slopes go from really big positive values to more moderate positive values, eventually 0, moderate negative values, and eventually really large negative values, right? So what are the slopes doing? Going from really positive to really negative, they are decreasing. So f prime is decreasing. And f prime is decreasing when f double prime is less than 0. Okay? Do you want a really quick way that might help you remember this? I don't have candy for you. I'm sorry. But I have a nice little quick way of helping you remember this. Right? This is a little bit of philosophy, guys. You ready? In life, I want you all to be concave up. I want you to be concave up. What? No, that's not. No, right now, is the low point is not actually the lesson here. Good point. But the idea here is you always want to be concave up. The nose is the greater than symbol. I learned that last hour. I put a weird nose on it, and they disagreed with my nose, so I made it a greater than symbol. Because here's the real lesson, guys. Concave up makes a smiley face, and f double prime is greater than 0. F double prime is positive. And how can you look at a smiley face without getting just a little bit of positivity? Right? Right? Here's the other reason I want you in your life to be concave up. Are you ready for this one? This one you're going to love. I always want you to be concave up because even if you're falling, even if your slope is negative, very soon you'll be on the rise. Think about it. Think about it. Be concave up. Doesn't mean you're not going to have bad days. Doesn't mean you're not going to have bad days. But if you're concave up, pretty soon you'll be on the rise again. Okay? I could be a motivational speaker, but unfortunately I'm not qualified. I'm only qualified to teach mathematics, and even that is in question. All right. Same idea here. Same idea here. Concave down. Some frowny face. Why? Because f double prime is negative. It's a trick. I mean, the people that grade your exam might be entertained by that, but it's not going to be worth points. All right? I know. I wish you could be worth points too. If I was grading the exam, I'd get points for that. That's why they don't let me grade the exams. So concavity tells us whether a graph is whether the derivative is increasing or decreasing, and the second vocab word for today is inflection point. An inflection point is a special kind of point where the graph changes concavity. And from an argument, or from a concavity. From a justification standpoint, you need to justify inflection points the way you justify maxes and mins. Yesterday we talked about justifying a max and a min because if we have a min value at C, that means the derivative changed from negative to positive, right? We talked about that yesterday. A concavity change, an inflection point, has to occur where f double prime, if you will, where f double prime changes sign. And you need to check to make sure that it changes sign. If you think you've got an inflection point, you've got to check the double derivative on the left and on the right. And if it changes sign from positive to negative or negative to positive, you have an inflection point. Here's what they look like. Draw some pictures for me, will you? Do you see where the graph might change concavity? Over on the left, the graph is what? Concave. Down. On the right, the graph is concave. Up. Somewhere in the middle here, and you're going to be able to use calculus to identify it, somewhere in the middle, there is an inflection point. Okay, a couple other examples of inflection points that connect to things we've done already. We know about this x cubed graph that doesn't have a max or min at a critical value. What can we call that point now? An inflection point. Why? It changes from concave down to concave up. That is a point of inflection. X to the 1/3 also has one, guys. See it? The point of inflection right there. That's x to the 1/3. Just a couple of little pictures to help you connect the things we've already done. Good so far? Put on your concave up faces. We're going to do some examples pretty soon. Okay. Now, how can this? The next question is, how can this help us? What we've done with what we did yesterday. With what we did yesterday, on some particular functions, you can bypass the first derivative test, and you need to know the first derivative test. But on some particular functions, you can bypass it because the second derivative will tell you about the graph's concavity, and the graph's concavity will, I think, pretty soon, for obvious reasons, tell you whether you've got a max or a min. Okay? This graph right here, talk about it. It is what? Based on today's language. It is concave down. If I knew there was a critical value on an interval, critical value means slope is 0. If I knew there was a critical value on an interval, and I knew that the graph on that interval was concave down, how many options do I have for what type of critical point it is? What does it have to be? It's got to be a max, right? With me on that? How do I know? That point right there, f prime equals 0, and f double prime is less than 0. Those two qualifications together, neither one of them by themselves, those two qualifications together determine that I've got a local maximum point. That's the second derivative test. Is that easier than the first derivative test? If you know the second derivative, it is. If the second derivative is really messy, you might have to resort to other means. Okay? Similar idea over here. Describe this graph to me. That's concave up, isn't it? If I had a critical value right there, f prime equals 0, and f double prime is greater than 0, there's only one type of point that can satisfy that. What does it have to be? It has to be a local min. I should put the word local in front of this one too, guys, because I don't know that it's an absolute max, do I? Okay. I can only determine local mins and maxes at this point. Good? So the second derivative test is this. If f prime of c is 0 and the second derivative is negative, there's a max. Why? Because second derivative negative is a frowny face. If f prime of c is 0, meaning I have a critical value, and f double prime is greater than 0, I've got a minimum because double derivative greater than 0, f double prime greater than 0 makes a smiley face. Good? Oh, they both say max. Let's make this one a minimum then, because that's not the right word. That's got to be a minimum. My bad. Must have been a copy and paste thing. Okay. Might be a shortcut for you. Okay, but I'm going to review what we did yesterday anyway, because I think it's still important to have that, because either one of these, they might both be applicable. Not every problem can you do either one. So let's take a look. Questions conceptually before we do that? We are given the equation for a derivative. Do we know anything about f? Not really. We might have some general sense of what f is, but at this point we're given an equation for the derivative. So, A, identify where the extreme values occur. What do we have to do to identify where extremes are? Set what equal to 0? F prime equals 0. So to identify where extrema occur, I'm going to say that 4x cubed minus 12x squared equals 0. Why did I do the equation given instead of the derivative of the equation given? Because Already gave us f prime. Good. Okay. All right, let's factor. What can we take out? 4 and x squared. That leaves us with x minus 3. So the critical values are x equals 0 and x equals 3. Based on what we talked about yesterday, that's the next logical step, right? First derivative test. I'm going to show you in a little bit that the first derivative test isn't always necessary. Depends on what they're asking you. Okay? All right, let's check those three intervals for f prime. Keep in mind that this is f prime. That's f prime, right? Let's put in -1. F prime of -1 is 4 times -1 squared, which is 1, times -1 minus 3, which is -4. Positive value or negative value? Negative value for f prime, which means f is decreasing. I'm going to go ahead and do that. Good. Let's check f prime of +1. Well, that's 4 times 1 squared times 1 minus 3, that's -2. That is a first derivative is negative. Do I have a max or a min there? Neither, right? It's not a max nor a min. It's falling and then it's falling again. That doesn't make a max or a min, right? In order for it to be a max or a min, the sign needs to change. That's the defense we talked about yesterday. Okay? Let's check f prime of, I don't know, 4. That would give us 4 times 16 times 1. Positive or negative? Positive, right? Okay. So based on our, I'll go down here to part A. We'll do B and C and D in a minute. There's not a ton of space on the smartboard. I'm going to have to deal with it. So at x equals 3, we have a local what? Min. Why? Because f prime changes from negative to positive. That's the defense they're looking for on the exam. Okay? X equals 0, there is no extreme. Why? Sign didn't change. F prime did not change sign. Okay? Can we answer B now? Can we answer B? Let's do increasing. What work am I going to use to defend my work on increasing here? What am I going to use? I'm going to use the number line I just made, right? So what intervals is f increasing? 3 to infinity. 3, infinity. What intervals is it decreasing? Be careful on this one. Negative infinity to 0 and 0 to 3. Is it increasing or decreasing at 0? Neither. Neither. Either. Either. It's neither. Increasing nor decreasing. Good there? So really, part A and B were a review of what we just did yesterday. How's that going in context? Does that help? Almost done. We're going to do C and D, and then we're going to call it. Okay? C says find where the graph is concave up and where it is concave down. What determines concavity? F double prime. So let's do this. For part C, we're going to go ahead and find f double prime and set it equal to 0. F double prime of x is 12x squared minus 24x. Set it equal to 0. Take out 12x. That leaves us with x minus 2. So I got x equals 0 and x equals 2. Are those 2 points inflection points? Maybe. What do we have to do? We have to test it. So I'm going to make, and this is going to seem a little confusing at this point. Gosh, Mr. Best, why would you use another number line? Well, they seem to work. So I need to check. I need to test to make sure that it changes concavity. So let's check f double prime of negative 1. That's negative 12 times negative 3, which is a positive value, right? Concave up. Let's go between 0 and 2. F double prime, sorry, I put F prime on that one. That should be F double prime. It should be F double prime. It looks like F prime. F double prime of positive 1. That's 12 times negative 1, right? That is a negative value. So I can draw pictures here. First region, concave up. Second region, concave down. Third region, let's do F double prime of 3. That's 36 times 1. That's a positive value as well, so it's concave up. Went through that kind of fast. Does that make sense, though? So it's concave up on the intervals from negative infinity to 0, and again from 2 to infinity. And it's concave down from 0 to 2. My work is kind of filled up the page here. Does that make sense, though? Okay. For the last step, we're just going to put those two things together and sketch a possible graph of f. I'll go back to our number line, and I'll try to do it really small in this region right here. I'll go back to our number line. Maybe do it in a different color. Okay. My important points occurred at 0, 2, and 3, right? It's falling from negative infinity to 0, and it is concave up. So from negative infinity to 0, I'm going to be falling and concave up. Now the height of this graph doesn't matter that much. It can be down below the axis if you want it to be. So from negative infinity to 0, it's falling and concave up. Good? That would hold water if I were to pour water into it, so it's concave up. From 0 to 3, it's falling again. But from 0 to 2, it's concave down. So from 0 to 2, it's concave down and falling. And then what happens at 2? It becomes concave up. Is it still falling, or is it changed to rising? It's still falling, right? The function is still decreasing because I've got negative slopes there, negative first derivatives. So there's an inflection point there, and then it becomes falling but concave up. And at 3, we already determined there's a local min, so the graph is going to rise after that. Okay? There is a possible graph of f. Now, the vertical alignment of that graph doesn't matter at this point. It can be anywhere aligned vertically. But the key here is your first concavity change has to happen at 0. Your second concavity change has to happen at 2. And your min value has to happen at 3. Question. It goes back up because for the end of the graph, the slope is positive, and I've got a min at x equals 3. Okay? All right. Homework-wise, don't spend a ton of time on homework over break. I don't want you to bog yourself down with calculus. Some of you may have already discovered that number 27 on day 1 is a bear. You don't need to worry about it at this point. Try to do some of the self-check problems, and then just pick a handful of these to do before you leave. We will have a formative quiz, 15% quiz, probably Tuesday after break. So Monday we'll come back and review a little bit and get your brains ready for first derivative test and second derivative test again. We'll do smiley faces and frowny faces again, right? And then we'll we'll quiz Tuesday.